Please take a look at this. We have 5 vectors. Question: find a basis and the dimension of their span. Well, observe that span of these vectors is a vector space. How to know its dimension and how to find its basis? We use this theorem that tells us that in order to find basis and dimension, we put all vectors together, find an echelon form, and then look at pivots. It's exactly what we do here. We put all these vectors together, we apply elementary row operations in order to come up with an echelon form, and now we see pivot columns are column number 1 and column number 2. Therefore, vectors v1 and v2 form a basis of this vector space, and therefore the dimension of this vector space is equal to 2. Any questions about A?
Yeah, I have a small question. The third column, it is 2, -3, and some non-zero value. Would the dimension be 3 and the basis?
Absolutely. If instead of this 0 we have some non-zero numbers, then vectors v1, v2, v3 form a basis, and therefore dimension is 3. Other questions?
Professor, this is a general question, but what does reduced echelon form show us that echelon form does not?
Yes, very good question. So let us go back. Here is echelon form. Here is a reduced echelon form. Reduced echelon form means instead of black squares, we have ones. And now above each pivot 1, we have zeros. Question is, why care about the reduced echelon form? Answer is, if you see that our system has infinitely many solutions, in order to find these solutions, keep applying elementary row operations in order to obtain the reduced echelon form. Does this answer your question?
Yes.
It's exactly what we did in all these examples. Echelon form tells us that our system has infinitely many solutions. Therefore, we keep applying elementary row operations in order to come up with a reduced.
To solve the system.
Yes. Here again,
Awesome.
echelon form, reduced echelon form.
Can you repeat like the last few things you said, please?
So, question was, why care about reduced echelon form? Answer: if you solve a system using the augmented matrix method, and if you see that your system has infinitely many solutions, keep applying elementary row operations in order to obtain the reduced echelon form that allows us to describe all solutions of our system easily. Was that your question?
Yes, thank you.
Other questions?
So since there are less pivots than columns,
Yes.
does that mean these are dependent vectors?
Yes, absolutely. So this theorem says that if the number of pivots is lesser than the number of vectors, vectors are dependent.
So vectors 3, 4, and 5 in our last example, are those like the extraneous vectors, I guess?
Well, here's the logic. Observe that this vector space is two-dimensional. Since our vector space is two-dimensional, any 3 vectors from this vector space are linearly dependent.
Okay, cool.
Next, In B, we ask the following questions. Do these vectors span R3? Let us go back to this theorem again. It says that vectors v1 and so on, vm, span Rn if and only if an echelon form has a pivot in every row. Let us take a look. Do we have a pivot in every row? No, there is no pivot here. Conclusion, our vectors do not span R3. Any questions here?
So what would be the span? R2?
R2, yeah.
No, they do not span R2 because these vectors are not from R2 at all, because R2 is the set of all matrix columns with 2 rows. Here we have 3 rows.
Oh, so it's either Rn or it's nothing.
Well, they span their span. They just don't span R3. Span of these vectors is not equal to R3. That's it. And of course, it's not equal to R2 because these vectors are not from R2 at all.
Right, that makes sense. So how would you find the span of this? Or is that beyond this class? You said it's not R3. So like, what is the span?
Well, we can come up with a geometric interpretation. Observe that the whole vector space can be spanned by these 2 vectors because these 2 vectors form a basis, correct?
Right.
But now, what is this geometrically? Geometrically, these 2 vectors are 2 non-parallel vectors in R3. What is their span? Their span geometrically will be a plane that goes through these 2 vectors. Done?
Mm-hmm. That makes sense.
Next, in C, we want to find all solutions of this homogeneous system, where A is this. So we apply the standard procedure. We put all vectors together, we add the 0 column, because we are talking about the homogeneous system, and we apply elementary row operations in order to obtain first echelon form, then reduced echelon form. After that, we switch to the corresponding system. We leave all basic variables on the left, and we move all free variables to the right. After that, we start with a matrix column that consists of variables x1, x2, and so on, x5. We leave all free variables without change. We replace all basic variables by the corresponding expressions. Done. And then we split this single matrix column into 3 pieces. Here is a complete description of all solutions of our system. Lastly, D, find a basis in the dimension of the vector space of the solutions of our system. Well, first of all, observe that indeed the set of all solutions of this system is a vector space, because the set of all solutions of our system is span of U1, U2, U3. The set of all solutions of our system coincides with the set of all linear combinations of these 3 vectors. Therefore, it's a vector space by theorem 2 from section 3.2. Important remark: if instead of a homogeneous system we have a non-homogeneous system, the set of all solutions of any non-homogeneous system is not a vector space at all. One of the reasons, there is no 0. 0 is not a solution of a non-homogeneous system. because if you plug in 0 into the left-hand side, the result will be 0. But we are talking about non-homogeneous system, which means the right-hand side is non-zero. Repeat once again. If we have a linear homogeneous system, the set of all its solutions is a vector space. However, if we consider a non-homogeneous linear system, the set of all solutions of such system is not a vector space. So once again, here we're talking about a vector space. What is its basis and dimension? Well, guys, it is easy to show, and here we show that these three vectors are independent because there is a pivot in every column. Therefore, basis is u1, u2, u3, and therefore dimension is 3. Compare. In A, dimension is 2. In D, dimension is 3. Furthermore, in A, dimension is the number of pivots. In D, dimension is the number of non-pivot columns, the number of free variables. Now questions.
Can you explain what you mean by non-pivot columns, please?
Non-pivot column is a column where we do not have a pivot. Please take a look at this. Here's pivot number 1, here's pivot number 2. Therefore, column number 1 is a pivot column, column number 2 is a pivot column. This is not a pivot. This is not a pivot. This is not a pivot. Column number 3, 4, 5 are non-pivot columns. Therefore, x1 is a basic variable, x2 is a basic variable, but x3, x4, and x5 are free variables. Does this answer your question?
Yes, thank you.
Let me give you the following remark. On tests, you can skip this part because it is known that once we solve our homogeneous system and write our solution as this, then these matrix columns will always be linearly independent. In other words, dimension of the vector space of solutions of this system is equal to the number of free variables. Guys, questions here?
Where did the last column of zeros come from?
We are talking about homogeneous system. It comes from this.
Oh, okay.
Other questions?
Wait, I just want to confirm the dimension of the solutions of the vector space is the number of.
No, excuse me, not solutions of the vector space. Dimension of the vector space of solutions. In other words, let us find all solutions of this homogeneous system. We have a set of solutions. This set is a vector space because the set coincides with all linear combinations of these three vectors. Since this is a vector space, we ask a question about its basis and dimension. Basis is u1, u2, u3, dimension is 3.
Okay, yeah, that confirmed my question. Thank you.
Other questions?
Is the number of, or I mean, is the dimension the number of free variables?
It depends on dimension of what you are trying to find. Dimension of this is the number of basic variables. Dimension of this is the number of free variables.
Okay.
How do we know which like when the dimension is equal to free variables and when it's equal to basic variables?
You have to look at the question. Here we find a basis of span. Here we want to find a basis and dimension of the vector space of solutions. Does this answer question?
Yes, thank you.
One last topic is this corollary, which is of a great importance in the next section. Before we discuss the corollary, please take a look at theorem 11. Suppose A is a square matrix, and suppose its determinant is not equal to 0. Since determinant is not equal to 0, A inverse exists. If we multiply both sides of this equation by A inverse, we will get this, correct? Conclusion: if determinant is not equal to 0, our system has a unique solution. Case 2, suppose determinant is equal to 0. Then we have two other possibilities: no solutions or infinitely many solutions. But now please take a look at the corollary. To the contrast with theorem 11, in this corollary, we are talking about homogeneous systems only. So once again, suppose we have a homogeneous system. Note that any homogeneous system has at least one solution. The trivial solution, 0. Therefore, if in theorem 11, instead of B, we have 0, this is not the case. If in theorem 11, instead of B, we have 0, we exclude this possibility, because a homogeneous system always has a solution. Now, suppose we have a homogeneous system and determinant is equal to 0. Then this is not the case either, because we have this case if determinant is not equal to 0. Which means, if determinant is equal to 0, our homogeneous system cannot have a unique solution. So, if we have a homogeneous system and determinant is equal to 0, this is not the case, and this is not the case. Therefore, the only possibility is this. Let's put pieces together. If we have a homogeneous system where determinant is equal to 0, it has a non-trivial solution because it has infinitely many solutions. Moreover, this is if and only if statement. Our homogeneous system has a non-trivial solution if and only if its determinant is equal to 0. And here is an example. We have a homogeneous system. Question: for which values of lambda this system has a non-trivial solution? We know that a homogeneous system has a non-trivial solution if and only if the determinant is equal to 0. So we find the determinant of this matrix expanding by a row number 2. Done. We simplify. Determinant is a lambda minus 1. Lambda minus 1 is equal to 0 only if lambda is equal to 1. Conclusion: this homogeneous system has a non-trivial solution only if lambda is equal to 1. Folks, any questions here?
Wait, can you repeat how we went from the first step to the second step?
Yes, so question is, for which values of lambda this homogeneous system has a non-trivial solution. By the corollary above, we know that our homogeneous system has a non-trivial solution only if the determinant is equal to 0. So let us find the determinant. After all simplifications, we get a lambda minus 1. Obviously, a lambda minus 1 is equal to 0 if a lambda is equal to 1. Does this answer your question?
Yeah, it does. Thank you.
Other questions?
Would another way to solve this is by noticing, well, you need the determinant to be 0, and the left column is 1, 1, 1. So we can just make lambda 1 directly, and you would have 2 columns of the same thing.
Yes and no. Sure, if you plug in 1 instead of lambda, the determinant will be 0. But question is, are there other lambdas? You see what I mean?
Right, right. So the number 1 is a viable solution, but there could be many more.
Exactly. So therefore, the best way to solve it is to find the determinant.